Okay, thank you. Welcome back. Good afternoon. So in the first part, we approached F-theory from a type GB perspective, and we showed that the profile of the exodilaton is equivalent to an elliptic vibration over the physical compactification space Bn. And importantly, in this language, the elliptic fiber is really an auxiliary object. It's an auxiliary curve whose complex structure encodes this physical field tau. Now, as we said, there is an alternative way of approaching such F-theory compactifications via M-theory duality. So we'll be discussing from M-theory to elliptic vibrations now. So the second route, not via the 7 branes, but from the M-theory directly. Which in particular will give a different perspective on the structure of the elliptic fiber. So by M-theory, we will be meaning essentially the long wavelength limit of 11-dimensional supergravity. So we consider 11-dimensional supergravity with bosonic field content, the 11-dimensional metric GMN, the 3-form gauge potential. This is crucial. 3-form gauge potential, C3, which is invariant under a shift C3, which enjoys a gauge symmetry. C3 goes to C3 plus d lambda 2. So it's a higher form gauge potential, and consequently, the field strength G4 equals D3 is gauge invariant, clearly. So the effective action in 11 dimensions is at the bosonic level 2 pi over the characteristic length scale in 11 dimensions to the power of 9. And then we have the Einstein-Hilbert term. We have the kinetic term for the gauge potential. We have a Chern-Simons term, which is of some importance. And then there are higher order terms, which in fact will also feature later on, plus order 2 pi over L11 to the 3, which come with 6 extra powers of length, as we will be discussing briefly. So that's the effective action of 11D supergravity. And this will couple, in particular, to the M2 brane. So that's a second key player, not only the 3-form potential, but also the M2 brane, to which C3 couples electrically. C3 couples electrically to M2 branes. So the action of the M2 brane has again a dBi type part, 2 pi over L11 cubed times square root minus determinant, plus then the electric coupling, of course, integral C3. And the duality is now a fiber-wise duality of the well-known duality between M-theory on a torus, this is where this torus appears, and type 2B string theory. So let's consider first M-theory in that sense, so 11D sugra on a torus T2, which now we think of in down to Earth terms as the product of two cycles, S1A times S1B. Just reviewing this is well known, where S1A we take to be the M-theory circle. So S1A is the M-theory circle of radius RA and associated with coordinate x. So it's not the coordinate x of the Weierstrass model, but let me just now introduce a coordinate x. So this means that, of course, as we take the circle R, the radius RA to 0, we approach type 2A theory on the space R18 times S1B. So as RA goes to 0, we approach, in the usual fashion, type 2A string theory on R18 times SA, where crucially the component of the metric along the circle direction, G1111 so to speak, is related to the dilaton of type 2A, and G11 and the remaining ones will translate into the C1 Raman-Raman potential of type 2A. Question? That's right. Thank you very much. So G XX will be related to phi in type 2A, and Gx, and then the remaining components along R18 times S1B. This is related to C1, the Raman-Raman one-form potential in type 2A, according to the usual type 2A M-theory duality. And then the second standard step is to now perform a T-duality from S1B along S1B to go from type 2A to type 2B. So we T-dualize on S1B. So we get type 2B string theory on R18 times the dual circle with dual radius RB tilde equals LS squared over RB. And in particular, so S1B has coordinate y. And in particular, C1 in the y direction under T-duality becomes C0, because we remove the leg along which we T-dualize for the Raman-Raman fields. So as our B tilde goes to infinity, we therefore recover type 2B on R19, where C1 in the y direction, in the original y direction, becomes C0 of type 2B. And also the other fields transform in the usual way under T-duality. So M-theory on R18 times T2 is dual in the limit where the radius of RA goes to 0 and RB goes to 0 to type 2B on R19. Say again? Such that the it depends on, well, if I don't take it, well, it depends on what the, no, not necessary. This will then affect the exodilaton in type 2B, and if it diverges, it diverges. So it will be okay to have diverging exodilaton. So there's a more precise statement that I'm going to give now that should address this. So this is just the easy way to memorize things, but one can do this much more in much greater detail and write down this dimensional reduction of M theory on a torus in great detail, introducing the metric on the torus and following in detail how one gets from M theory to 2A and then back to type 2B. This has been done in many places and beautifully reviewed, in particular by Denev's lectures, Lesouche lectures. So I'm just quoting this because otherwise I would have to just copy it because it's perfect. So you can read this up in those lectures on page 24, 25. And you find that maybe I should, yeah, I'll stay here. So if we start, no, let me go over there. Sorry. So if we start with M theory on R18 times T2, where the torus T2 has complex structure tau equals tau 1 plus I tau 2, and volume V, then this is dual to type 2B on R18 times S1B. I guess I should call this S1B tilde, indeed, with exodilaton tau equals C0 plus I over GS. So the complex structure translates directly into the exodilaton. And we have an Einstein frame metric ds squared equals type 2B in the Einstein frame. This is the flat metric in R18 plus Ls to the 4 over V, V being the original volume, times dy tilde squared, where y tilde is a coordinate on S1b tilde with periodicity 1. So you have to keep track of the factors and factors of Ls and do the duality in detail. So in particular, this shows that as we take V to 0, V being the original volume, the prefactor here of dy squared goes to infinity. So this means that in this limit, the fact that y tilde had periodicity 1 doesn't matter anymore. So this becomes just then, in that limit, the 10-dimensional type 2B action. And it is in this sense how the complex structure and the volume in M theory enter. So if the complex structure is such that there's a degeneracy, this means then that the exodilaton would degenerate, like is expected in particular in presence of 7 branes, where we have these logarithmic problems and also others. So as V to 0, we recover type 2B on R19. And I should say, as V to 0, while Ls stays fixed, we recover this type 2B. This is sometimes important to take into account when it comes to really tracing back how the duality works. Okay, so this is this fiber-wise duality between, or this is just this duality between R18 on type T2 M theory and type 2B. And it's useful to keep this in mind, this statement, that really this extra circle comes with a factor of 1 over V, because that implies then what happens in the limit V to 0. And again, a little bit of work is required to do so. It's 2 pages. We can read it up there. So now the logic is to promote this to a fiber-wise duality. So suppose that the M-theory space-time is in fact a torus fibration, and fiber-wise do this duality to type 2B. So we would promote this to fiber-wise duality so we would have M theory on R1, 8 minus 2n times yn plus 1, complex dimension of an elliptic fibration, where yn plus 1 is an elliptic fibration, so pi e tau yn plus 1 over bn. An elliptic vibration, or in fact a torus vibration, is sufficient. We'll discuss the difference briefly in a second. This is a torus vibration. Then this is dual to type 2B, indeed, on R1, 8 minus 2n times Bn, so times S1B tilde times Bn, with metric ds squared equals ds squared R1, 8 minus 2n plus ls4 over v dy tilde squared plus ds squared bn. And the complex structure tau of e tau, which in general can now vary because we're looking at elliptic vibration, maps into the exodilaton tau of type 2B. And in particular, note that we start on this side with M theory on a space, but M theory without any further addition. So in order to preserve supersymmetry, this space yn plus 1 has to be Calabi-Yau. To preserve SUSY, the same amount of SUSY as from the 2B perspective, this is then automatic. In M theory, without further ingredients, so no particular backgrounds or anything, yn plus 1 must be Calabi-Yau. So we see again that the elliptic vibration has to be Calabi-Yau space, even though the derivation is slightly differently. From the M theory perspective, it's immediate. From the 2B perspective, we had to work much harder to arrive at this. And there are 2 points I'd like to stress in this context. The elliptic fiber, from the M theory perspective, is part of space-time. So in the M theory, the elliptic fiber is just part of the full space-time on which we compactify. And so one of its cycles goes away, one of its circles goes away by going to type 2a, and the other circle becomes part of the extended type 2b space-time, the extended part, in the limit where the volume goes to 0. So E tau, the elliptic curve, or the elliptic fiber, is part of space-time in M theory. And one of its directions becomes part of space-time in type 2b via this duality. This is very different from the role the elliptic fiber played in our type 2b derivation, where it was just an auxiliary curve. And the second part, if we just consider M theory on that elliptic fibration, we don't care about F theory at all, then both the volume and the complex structure of the torus fiber play the role of a dynamical modulus, as always. However, the F theory lift, or the F theory limit, is the one where the volume V goes to 0. So it is only in this F theory limit that we forget about the information of the volume. So in that limit, this will not correspond in F theory, on that dual side, it will not correspond to a geometric modulus of the F theory compactification. Only the complex structure, tau, will correspond to a modulus or to a field in the type 2b picture, namely precisely the extra dilaton. So in M theory, both tau and V are dynamical moduli. So in the F theory limit, which is the limit V to 0, only tau is retained. Only the tau information is retained. So what we do in this approach is we compare, say, an F theory compactification. Say, let's take n to be 3. Then we would have an M theory compactifications to 3 dimensions. And we compare it with the type 2b compactifications on 3 dimensions times a circle. And in the limit where this circle goes to infinity, this is the limit where the volume of that fiber shrinks to 0. So that's another useful way of putting it. So an equivalent formulation of this duality would be that if we consider the effective action of M theory on an elliptic fibration yn plus 1 in R1 8 minus 2n, with the volume of the elliptic fiber being some modulus of the fibration, the modulus V, then this is the same. This theory in R1 8 minus 2n is the same theory as type 2b on Bn, being the base of the space, further compactified on an extra circle, S1, whose radius is 1 over V. Circle reduction of type 2b on Bn in R1 8 minus 2n times S1 b tilde, with the radius RB tilde equals Ls to the 4 over V square root. So type 2b, reduced on a circle, is dual to M theory on that space, on the elliptic fibration. If the radius goes to infinity, the volume of the elliptic fiber goes to 0 on that side. And then the information about the volume is lost. And in that limit, it's not a dynamical modulus. Okay, questions?
So at this point we have no seven brains in the 2B picture.
Not really yet. So indeed. So we know that since tau is varying, there must be a source to it. So we will be interpreting this as a as a seven brain language. So on the type 2B side, the type 2B theory is the one that we discussed. But in the M theory picture, there are no seven brains at all. And we will see where the gauge degrees of freedom on the seven brains come in now from the M theory perspective. This will now be the job to understand. Please.
Are you going to say what the difference between torus vibration and vibration?
Yes, now. Very good, very good. Okay. Okay, and we will do this now in chapter 2. Now that we've introduced the key players, we'll discuss the hand in hand, hopefully, the physics and mathematics of elliptic vibrations. And we'll go slow. We start with the smooth Weierstrass model, and then we find our way ahead. So, an elliptic vibration is a torus vibration with a section. So an elliptic vibration is a torus vibration with a section sometimes called zero section S0, and such a section is in general, meromorphic map from the base to the fiber. So in general, meromorphic. Here, to begin with, even holomorphic in the smooth Weierstrass model, map from the base to the fiber. So torus vibration just has a torus in the fiber. But for the elliptic vibration, so the elliptic curve is a torus with a marked point. An elliptic vibration is a torus vibration with a marked point everywhere, and that marked point everywhere is precisely the image of the section. So the section, section is a map from Bn to the elliptic fiber. So every point in the base B is mapped to some S0 or to some, okay, what's a good notation now? Let me call it like this, is a sigma of B in B tau. And this sigma of B is the origin, the marked point on the elliptic curve. So, to every torus vibration, so a priori it is sufficient to have a torus vibration for M theory and also for S theory. However, to every torus vibration, one can associate an elliptic vibration called its Jacobian, possibly at the cost of this vibration being singular in higher codimension such that no Calabi-Yau resolution of the singularities exist, which, however, is not a problem. So to every torus vibration, that's a fact, one can associate a possibly singular Weierstrass vibration, elliptic vibration. So there are therefore two possible perspectives one can take. Either one says, I'm happy from now on to discuss only elliptic vibrations, possibly at the cost of dealing with those singularities, which I may not be able to resolve into Calabi-Yau space. Or I say, I should really be looking at a torus vibration and study those. Both is in the F-theory limit equivalent, not in the M-theory. And for simplicity, I will from now on, so to speak, implicitly take the second point of view. I will now be focusing on elliptic vibrations, which is still maximally generic, as long as I allow for those singularities. And I will refer you to Miriam's lecture on Friday, where she will be discussing torus vibrations as well. So for simplicity, we assume, for now, the existence of a section. And again, this is actually not really a restriction, as long as we are happy with having those singularities. For the physics of torus vibrations without, see the lecture by Miriam on Friday. So the upshot is one can get the same physics, of course, by either looking at these possibly at these singular Weierstrass models, singular elliptic vibrations, or the torus vibrations. In both cases, it gives the same physics in F-theory, not in M-theory, but in F-theory they are the same. That's why, for us now, it's not a restriction to go to this. And we will see where the section comes in, where the existence of the section comes in, and what it means. Is this clear? The logic, at least, statement? No? Question? Are you okay? No, because you raised this. Was that clear? Okay. Okay. Thank you. Okay. So every elliptic vibration is birationally equivalent to a Weierstrass model. So every elliptic vibration can be written in this Weierstrass form, but up to birational equivalence, this means up to differences in higher codimension possibly, is birationally equivalent to a Weierstrass model. And birational equivalence means it's isomorphic up to loci in higher codimension. Higher codimension may differ, but for this purpose it's fine. So it could.
At a point, we have a Weierstrass model, and what's the ambiguity here?
The ambiguity is that there could be different types of fibers. Suppose you have a base, a 2 complex dimensional base, just then at points, codimension 2, there could be different types of fiber in the Weierstrass model compared to another representation of that model. And we will be classifying or reviewing the classification of the fibers in the Weierstrass model in elliptic vibrations which are not in Weierstrass form. There may be extra types of fibers in addition to that. But this happens in higher codimension. So away from those, the models are the same. And in the F-theory limits, they are all equivalent. Yes? In that case, indeed. So that is then a technical question for how to deal with those singularities, precisely. So that's why it is then useful to pass on to the torus vibration, but the set is this, I mean, one is not losing a model. One may have a representation of the model that may be more difficult or inconvenient to describe, indeed.
So, is this singularity a singularity of effect, or is this singularity
The latter. It's a degeneration of one of the cycles in higher codimension also. Indeed, precisely. So that's why the torus vibration is nice and smooth. The Weierstrass model is not smooth. Yes. So if we are able to deal with singularities, we don't care. Otherwise, it might be better, wiser to pass to the torus vibration to do computations. Yes. Okay, the Weierstrass model, of course, we introduced. Let me just, for completeness, write it down again. Maybe we don't need this since time is scarce. fxz4 plus gz6 equals 0 in a vibration in P231E. By this I mean this vibration of the coordinates x, y, z modulo the scaling relation over the base. Okay, so let's just briefly see where the section comes about. We know it because we say the section is a map that hits precisely the origin, so to speak, the marked point, the marked rational point on the fiber, and we know that this is just z equal to 0. So for all f and g, for all choices of f and g, there exists a rational point, so a point whose definition only involves rational functions in the fiber, which is given by, or a rational point actually, in the a rational point, yeah, in the fiber. But I mean, just about the notation. But I think we'll see what we mean. So given by Pw equals 0, this is my elliptic vibration, and then I cut out in this a locus z equal to 0. So when I put z equal to 0, then I have x and y. I have one rescaling relation between x, y, and z, and I can use this to arrange for x and y to be 1. In the fiber. So over each, that's why I hesitated now, over each point in the base, this defines for me a point in the fiber. Over each point in the base. So this is this extra point which always exists. And it's in the notes, so I mean, it's probably clear, but it's in the notes how to see that indeed this is just one point. So the locus S0 given by z equals to 0, this is a divisor, a one complex codimension object in the full vibration, given by precisely this point in the fiber, is a section on yn plus 1. And it intersects the fiber in one point. Namely, precisely this point.
So the problem mentioned earlier, like f is also 0 or something?
for all f and g, well, that's always fine. No, I mean, that point always exists. Yeah, if z is 0, then this goes away, and then we just have y squared equals x cubed. And that precisely corresponds after rescaling to 1 point. So we have the situation that we have here the space, Bn, and we have the elliptic fiber over it. And over each point in the base, so here we have another elliptic fiber, different shape. Over each of those points in the base, over each point there is 1 point in the fiber that I can label by saying this is z equal to 0 intersecting the fiber. And that's what the section is. It's a map that maps each point in the base to this point in the fiber. And we'll see in a second why this section, what the physical role of the section is in empty radiality, f-empty radiality. Okay. Okay, so of particular importance in elliptic fibrations, question? No. Both from the math and from the physics are those loci on Bn over which the elliptic fiber may become singular. So the fiber E tau becomes singular whenever we have Pw equals 0, that puts us on the Weierstrass model as such, and also the gradient of Pw equals 0 with respect to coordinates x, y, or z vanishes. That's the definition of a singularity. When you have a hypersurface in some space, then this hypersurface acquires a singularity. A singularity means that you cannot define the tangent space to a point. And this is so if the gradient vanishes, because then you don't know how to move again out of this point. That's what a singularity is. So a singularity of the fiber is one where the gradient vanishes in the fiber directions. So dp with respect to x and y or z is 0. At 1 point in the fiber. And this happens whenever the discriminant delta, which is 4f cubed plus 27g squared equals 0. That's the discriminant. So note f and g are now, we have an elliptic fibration, so f and g vary over the base as sections of a bundle, and there will be points where they satisfy this relation. And when this happens, then dp is 0. And I'm giving you the proof in the notes. The statement is simply that this dp equals 0 occurs when some of the roots, when 2 or more roots of the cubic in x here coincide. And this, by definition, is what happens when the discriminant of that cubic vanishes. And this is precisely the discriminant of that cubic. So you can, similarly to what happens when the 2 roots of a quadratic equation, they coincide when its discriminant vanishes. Here, these are roots of the cubic equation, x cubed plus x, essentially plus constant. So this is a condition which happens in complex codimension 1 on the base. So in complex codimension 1, there will be points where this condition is satisfied. This happens over complex codimension 1 loci in the base Bn. So we will have a situation where the fiber, and there's here some locus where delta equals 0 in Bn, and over these points something terrible will happen to the fiber. The fiber will be singular at one point, and this is usually drawn in this way. There is one singular point in the fiber over those points in the base. Now, suppose f and g are generic functions on the base. Generic in the sense that they are sections of a particular bundle, so they have to sit in a particular class, but I take all polynomials in that class such that f and g are maximally generic, so they don't have any particularly weird form. So for f and g generic, the locus delta equals 0 on the base, this cuts out a connected divisor, so codimension 1 object on Bn, which I drew already here. If f and g were non-generic, then it could be that it factors into several ones. And we'll discuss this in a second, but first let's stick to that case. So let's now look at what happens over this discriminant divisor in the base. So at a generic point on the discriminant delta, we have that on delta equals 0, we have that delta equals 0, but f and g by themselves will not be 0. This is at the generic point. So if I pick a random point on this discriminant, then only the discriminant will vanish because I put myself there, but f and g individually will not vanish. Question? No. It does not go through those singularities. That's important, and we'll come to this. So at generic points, and the torus becomes a singular object, it forms a so-called nodal curve. So you can let's take it take a real projection, so to speak, of that complex curve. It's an object which self-intersects once. This is also what I try to draw here. So this is now one complex dimension. It's just a curve which self-intersects once. This is called a node. And this fiber is called the I1 fiber. That's just the name in Kodara's classification of possible singularities. So this is the situation which happens, as we just said, over generic points. So where delta vanishes to order 1, that's the vanishing order of the discriminant, but f and g do not vanish. So they vanish to order 0. This means that they do not vanish. So that's the situation. So when f and g do not vanish, but delta vanishes just to order 1, it's just some polynomial equals to 0, then the fiber over this just becomes singular in the sense that it has one singular point where a self-intersection of this type occurs, called nodal curve. So i.e. e tau is singular at one point of self-intersection. But, and this is important, what vanishes here is only the gradient in direction x, y, z. So you can check this, dp x, y, z vanishes, but dp is non-zero in direction of the base coordinates. So the gradient in the directions normal to the elliptic fiber is not zero. So this means that the elliptic fiber is singular, but the fibration, but the manifold yn plus 1 is smooth. So therefore, yn plus 1 is smooth. That's why a Weierstrass model where f and g are generic in that sense is called a smooth Weierstrass model. So there are singularities in the fiber, but they are not singularities of the full geometry. Say again? Not zero, absolutely, thank you. Good. We'll come to this. It goes to I infinity, and this is because there's a 7 brane there, but we'll discuss that. Okay, it's I think now time to switch to this. So before I come to this physical interpretation, let me just complete this little classification. This is just for completeness now, but I want to do it. So just for completeness, let's go to the locus on delta. So we said on a generic point of delta, f and g of delta equals 0, f and g do not vanish. But of course, there can be a point where both delta equals 0 and f equals 0. That's a non-generic, higher codimension. At this point, also g vanishes, because delta is f cubed plus g squared. So this is just for completeness now, but let me briefly bring it. At f equals 0 and g equals 0, this is codimension 2 on the base, again with f and g generic. Also delta equals 0, which is 4f cubed plus 23 equals 0. And in fact, it vanishes now to order 2, because this goes like x squared, x to 0, x some coordinate, not the fiber. This one like x cubed, so it has an overall x2. So it vanishes to order 2. So we have now the situation order f, order g, order delta equals 1, 1, 2. The elliptic fiber at this point, where f and g is 0, takes just the form y squared equals x cubed. And this turns out is, again, a singular curve. It's a cuspidal singular curve. It's a cusp, something that touches itself at the singular point. Cuspidal curve. So again, one point of self-intersection, but in this tangent way, because y squared equals x cubed.
Sorry, what do you mean f and g generic?
So f and g take generic functional form. Is a generic functional form, but nonetheless, I can now look at what happens when f equal to 0 and g equal to 0 simultaneously. But without enforcing this by saying, so for example, not generic would be f equals omega times f primed and g equals omega times g primed. This would not be generic because it factorizes. It would satisfy this, but in a bad way. But it could, right? So if it's a generic function, there will still be zeros, but not enforced by such factorization. Or any further relations. There can also be more subtle relations between f and g, such that the coefficients of the polynomials c are related to coefficients of polynomials there. So I take random coefficients of all polynomials. So, and just for completeness, this is called type 2 fiber in Kodaira's classification. And again, we have the same situation, E tau is singular, but y n plus 1 is smooth. Okay, so the conclusion is the smooth Weierstrass model. So if I take a Weierstrass model with f and g generic, then I can have three types of fibers. I can have the generic fiber. I can have the fiber where delta is 0, but f and g don't. Looks like this. Or I could have this specialization where f and g both vanish. If I took an elliptic vibration not in Weierstrass form, then this list would be longer. Then I would find more types of fibers. This related on the Weierstrass form. This is meant by the statement that up to higher these are effects in codimension, up to codimension effects, they are the same. So for note, an elliptic vibration in non-Weierstrass form, has additional types. So, sorry, I should say a smooth elliptic vibration. So smooth in the sense that y n plus 1 is smooth, okay? In non-Weierstrass form has additional singular fiber types. In codimension, and therefore agrees with the Weierstrass model only up to those codimension loci. That was what I meant. Okay, so that was the classification of the smooth model, and now we come to the physics. That's, of course, crucial. Finally, the physics. What does this mean? And we'll give an interpretation first in the 2B picture and then in the M-theory picture and see how they match. So physics interpretation. Via type 2B. So the statement is that this locus delta equals 0 is the location of the 7 branes. Why is that? By doing precisely what you suggested, looking at what tau does at those points, and see how this matches with the supergravity solution of 7 branes with which we started. So to this end, recall that given a Weierstrass model, we can read off tau via this Jacobi J function. So there is a function j of tau, which is a modular form, and this is related in the Weierstrass model. So this is not the definition of the function. There's a function j of tau, which in the Weierstrass model turns out to equal, we had it on the board already, 4f cubed over delta, where delta is precisely this discriminant, 4f cubed plus 27g squared. And this j of tau enjoys an expansion in e to the 2 pi I tau of the type e to the minus 2 pi I tau plus order 1, 744, plus then 196, what? Okay, I don't have it on here. 196 something times order. Very good. E to the 2 pi I tau, famous number, plus higher order terms in e to the 2 pi I. So if tau, I mean, this is now a heuristic argument. If j of tau goes to infinity, plus infinity, then this is consistent with tau going to I infinity. So j of tau to infinity is consistent with tau goes to I infinity. Because of this. And indeed, at an I1 locus, so this generic point, f is non-zero, delta goes to 0, so this goes to real infinity. So this is what happens at an I1 locus. J of tau goes to infinity. This is finite by 0. So tau is consistent with tau going to I infinity. So tau was C0 plus I over GS. And we now compare this to situation for a 7-brane. For a 7-brane, we had that we had a logarithmic profile ln 1 over 2 pi I ln z. And that's precisely consistent with this behavior. So we see at the I1 locus, this is the one where f is finite, tau goes to I infinity, so GS goes to 0. And this is the behavior near a single D7 brane, or 1-0 brane. Because we had at the beginning tau of z minus z0 equals 1 over 2 pi I ln z minus z0 plus blah, blah, blah. There is also another way of saying the same thing. That would be the better way, but it would involve more machinery that I can't introduce now. Really, the 7-brane is defined by its monodromy on tau. And one can check that singular fibers of that type have precisely that monodromy. So this is part of the Kodaira classification. If you evolve the elliptic fiber around a singular fiber, its two cycles, the two 1 cycles, undergo a monodromy, which is precisely the SL to Z monodromy. And this way you can one-to-one pin it down. This is kind of, I mean, I don't know how much you trust this argument here. It's consistent with, but maybe not one-to-one, or it takes more time to show it at least. But it gives the right result. And with the monodromies, it works. It works explicitly. So more interesting, and I have not much to say about this, is the type 2 locus. So there we have J of tau is 0 by 0. So it's indefinite. It's not clear what it is. Indefinite. So here the monodromy argument would be better. And it turns out that this is a remnant, so to speak. This is something that happens in codimension 2 anyway, a remnant of, if you're familiar with this, the O7 plane in 2B language. So it's a locus on the brane where somehow the remnant of the O7 plane can still be seen in this way. So it's a non-perturbative locus. The usual one. Yeah, I mean, it depends on your notation, yes. The one with negative, everything negative, yes. Negative tension, negative charge. The usual, yeah, exactly. Okay, I give you, for this, I give you also a reference 09081572. Okay. And note, good. So the statement is, from the discriminant locus, one can read off the location of the 7 branes. And that is very useful. We had the question of why is elliptic fibration useful? Because without thinking, we simply compute where delta is 0, and then we know where the 7 branes are. And this is guaranteed to be a consistent configuration. If we thought about 7 branes without this language, then we would have to think very hard which types of branes can be consistently put together. These different type of PQ branes, which unfortunately I discussed only very briefly, they cannot simultaneously be present in a consistent way in all cases. And it's, in general, not known how to describe this consistently other than in this way. So the elliptic vibration automatically gives rise to the correct and consistent brane configurations.
Can you have singularities of higher frequency?
Yes. All of this is coming. You can. This is where matter lives. And the gauge group, we have a 7 brane. What's the gauge group? So in this case, as we see with F and G generic, we have just a single bound state of 7 branes in O7 planes. And it turns out that the gauge group is trivial. So naively, you might think that you might have a U1 gauge group because you have one 7 brane. But this is really projected out if you think in terms of type 2B by the non-perturbative version of the orientifold projection. So the gauge group G is trivial. So you would have a single bound state, non-perturbative bound state of a D7 brane with O7, the O7 minus plane, and the would-be U1 is projected out. So it would be very interesting to discuss this in greater detail. This is very, this statement at least is understood. One can discuss this by looking at the so-called Sen limit. I'd love to do this, but we don't have time. I'll give references where this is discussed. So this is a very entertaining exercise. If the D7 brane is in the class 8 times the O7 plane, it does. They're not homologous. One is in class 8 times the other.
So it's like an 8.
Yes, but not 8 separate D7 branes, but one D7 brane in class 8 times O7. So it wraps a divisor, which is in the homology class 8 times the other. And then it's fine. Upstairs, in the upstairs picture. So the gauge group is 0. Okay, so we are still practicing, right? This is a smooth vibration in the sense discussed, but we will then see that that there will of course also be situations with non-trivial gauge group, and then the full power of this will become apparent. Still, let's do this, the physics interpretation in M theory. No, I'm only saying that if F and G are generic, then this describes configurations of D branes in which there is no gauge group. So this is all for F and G generic. Okay, so F and G generic. We'll discuss the non-generic cases as next. But first, I need to describe how we understand this in M theory. Again, this is all preparation then for the singular case, but whatever we learn now will be useful then. So, in M theory, there is no 7 brane. So what's the origin of would-be gauge theory of would-be gauge symmetry from the M theory perspective? So in the effective action of M theory compactified of this elliptic vibration, gauge potentials come from dimensional reduction of the 3-form potential of supergravity with respect to harmonic forms. So in the effective theory in R1 8 minus 2n, if we complexify M theory, so we have that the gauge symmetry comes from the reduction of the M theory 3 form gauge potential C3. That's crucial. Namely, we decompose C3 in terms of a 1 form wedge, a 2 form, where the 1 form lives here. This will be a gauge potential. The 2 form lives on the internal space. And in order for this 1 form to be massless, the 2 form must be harmonic. So we need a basis of harmonic 2 forms. On the smooth, we call for f and g generic, we have the smooth Calabi-Yau y n plus 1. So the harmonic ones, H2 of yn plus 1. So since we are on a Calabi-Yau space, this is the same as H11 yn plus 1. There are no 2 zero forms. And since this is an elliptic fibration, every 1 form on the base is also a 1 form on the full space. So we have H11 of the base. And then, and this is now where the section finally comes in, plus 1, because this is this section. So here we have a basis, d alpha, on the base, so base divisors and their dual 2 forms. And here this would be the class of the section. If you had several sections, then you would have several such classes. But for now, we just have one section by assumption. So we can now look at the expansion of C3 in terms of those 2 forms, which live on the base, and this extra section, and see what it gives. So we can expand C3 equals A0 wedge S0 plus sum over all alpha from 1 up to H11 of the base times A alpha wedge D alpha B. We do this expansion, and A0 and A alpha will now be massless 1 forms in the M theory effective action. So in the M theory, they look like gauge potentials. So this seems to be in contradiction to what we said about the 2B perspective. But the key point is that we have now to compare very carefully those fields with their type 2B counterparts upon doing this F to M theory duality. So we now need to relate. Oh yeah, okay. So in M theory, we see that we have a gauge group U1 to the H11Bn plus 1 in M theory. But needs to relate these to F theory on Bn in R1 8 minus 2n times the circle. And then we see the following. We see 2 things. First of all, these 1 form potentials, they are associated with 2 forms on the base. So what else in type 2B now is associated with 2 forms on the base? If we think a bit, we know that we have a 4 form potential in the Ramon-Ramon sector of type 2B. We can also expand it along a 2 form, and we get then a 2 form potential in type 2B. If we take this 2 form potential and take 1 leg along the 1 cycle, we get a 1 form, and this is precisely the 1 form potential we saw there. So in other words, those which come from dB alpha are not gauge groups, in type 2b in F theory, but they are just the tensors which I get from reduction of C4 on the same two forms on the base. So these A alpha come from two-form tensors, B alpha 2, from C4 equals B alpha 2 wedge D alpha B, some alpha, where this is the Raman form potential in 2B after reduction on S1B tilde. So we match those one forms to actually tensors in type 2B. So they are not gauge groups in the F theory limit. They are gauge groups in M theory, but not in F theory. So that already shows us how the effective action of F and M theory can be very different. And second, and this is even more subtle, what about A0? Well, one does a circle reduction from 2B in order to get to M theory. The circle reduction automatically gives rise to a Kaluza-Klein U1. And A0 is precisely that Kaluza-Klein U1, which is there in the M theory, but of course not in the F theory, which is one dimension higher, because we decompactify that circle. So this is related to the Kaluza-Klein U1 from circle reduction. So more precisely, okay, let me just tell you that more precisely one has to shift the zero section by 1/2 of the canonical class on the base. If we do this, then the corresponding A0 is the KK U1. That's a technicality which will play no role for us. I give you the reference 1, 1, 1, 1, 2, 3, 5, 1. But that's just a technicality that has to do with some of the peculiarities. So we see that the M theory gauge group is much larger than the F theory gauge group. And if we subtract those, then we see that indeed in F theory we have no gauge group left in agreement. And again, note that this section here, A0, the zero section, is precisely related to this Kaluza-Klein U1. So we have no D-brane U1 in F theory limit. Question? Okay, so this was just this toy model of a smooth Weierstrass model. The next step, which we will do next time, will be to look at more complicated fibrations where F and G take a non-generic form. Then the list of singular fibers grows. And then we will find gauge symmetry, both in type 2B, because it corresponds to a non-trivial D-brane configuration, and in M theory, because we will find new two forms, essentially. So the game in M theory is really, give me all the two forms, and then you know about the gauge symmetry. And we'll discuss this. This will involve the Kodaira classification of singularities. And then we'll also see higher codimension singularities, which then give rise to matter. But review maybe this afternoon this logic in that context, because it will just be a theme with variations for the also for the proper and interesting case then with non-abelian gauge symmetries. Okay, so even if we do, so again, so there is a prescription to go from the torus vibration to the Weierstrass vibration called Jacobian construction in the arithmetic geometry literature. So even if one did not have an elliptic vibration in that sense, but only a torus vibration, on every torus vibration you have not a section but a multi-section. So you have a map from the base to several points in the fiber which get intertwined by monodromies. In those cases, instead, you simply replace this S0 by the class of that multisection. And this will still, so in particular this formula here, will still hold. This 1 now corresponds not to the class of the 0 section, but the class of the multisection. And likewise does the Kaluza-Klein U1. So from that perspective, it makes really no difference. So the physics is that the torus vibration, so the elliptic vibration, what is, okay, so the vibration, the geometry as such, sees the effective action of the M theory, not of the F theory. Because to the F theory, we have to go to this artificial limit. Now, in an M theory, we have, in the M theory effective action, we have degrees of freedom, Wilson lines, precisely around this extra circle from type 2B to M theory, which we can switch on. And in particular, there can be discrete Wilson lines, discretely many that can be switched on, which give rise to different vacua in the M theory perspective, all of which become equivalent in the F theory limit, because I forget about this full S1 vibration. And there can now be situations where a model in M theory has matter. So the elliptic vibration describes a model where there is matter in M theory which is not charged under any U1 gauge group, and which describes a different phase of this Wilson line compared to the torus vibrations. So, and the statement then is that since you have charged matter, since you have matter which is not charged under any U1, you cannot go to the Coulomb branch and resolve. This is a phenomenon which is exemplified there, but more general. And I actually wanted to discuss this then next time when we discuss the singularity. So the statement is so having a singularity means you have matter localized which is not charged under any U1. So there is no direction in the Coulomb branch which can make it massive without breaking supersymmetry. And that's precisely the statement that there cannot be a resolution. But we'll discuss this. Yeah, yeah. Perfect. Yes, of course. Absolutely. Absolutely. Yeah. Actually, I didn't want to discuss any of this. It was indeed. This is what will be discussed on Friday. Yes, yes.
So you said that tomorrow we will see some cases in which we have an elliptic and we have
actually, I wanted to discuss tomorrow the Weierstrass form singular, the singular Weierstrass form, and look at those singularities. Again, reserving the non-Weierstrass models to the Friday lecture. Up to birational, up to differences in the higher codimension. So this means that there will be two types of vibrations which agree everywhere except for, say, codimension 2 points, and in the base and the fiber over this. And then the type of this other vibration, which is not Weierstrass form, will have a fiber type which is not in this Kodara's list. And that's the situation.
Well, maybe one more question, yes?
So what do you mean by the 1/2? What do you mean by fractional?
This is in H11R. So, indeed. It doesn't matter, yeah. Yeah, it's an H11R. I'm only looking at the massless modes. Yeah.
So we will have a discussion session. We'll see how it goes. The only 2 lecturers present, and so we will stay in topic.
Hi. I just have a dumb question.